Should we begin the webinar, Rich?
Sure, it sounds good.
All right, good morning, everyone. My name is Rob Corcoran, and I'm InItech's Manager of Lean Manufacturing and Project Management. The goal of today's webinar is going to be to separate the hype from reality regarding Industry 4.0 and to identify areas where it could benefit the flavor and fragrance manufacturing environment. During today's webinar, at any point, feel free to submit a question in the chat window. After the time that we've spent discussing our main topics, we'll do our best to address as many questions as possible. Any questions that remain unanswered, we'll be sure to answer in a follow-up email and distribute to everybody who is on the attendee list today. Joining me today are Rich DiBernardo and Tim Cunningham. Tim Cunningham has extensive business, financial, and engineering experiences in the fragrances, food, and consumer packaged goods areas. During his career, he's held many different positions, including VP of Manufacturing for Bell F&F and Hartz Mountain. He has been the Director of Manufacturing for both Takasago and Bigelow Tea and was a plant manager for Nestle Flavors. Tim is a certified PE in chemical engineering, holds a Master's of Business Administration degree, is a certified Six Sigma Black Belt, and currently holds a position of Vice President of our Design and Build sector. Rich DiBernardo has 20 plus years of experience delivering best-in-class solutions to the flavor and fragrance plants around the world. He has visited hundreds of F&F manufacturing facilities and implemented hundreds of successful projects. Rich is one of the co-founders of Batchmetrics, and prior to InItech, Rich was part of the General Electric team as an automation specialist during the Jack Welch tenure. His experience at GE gave him a front row seat to the second half of the third industrial revolution. Rich is InItech's CEO and visionary, always pushing for a best-in-class solution and taking advantage of everything technology has to offer. So how do we get to Industry 4.0? As many of you know, the first industrial revolution began in England in the late 18th century. Following the invention of the steam engine by James Watt, the introduction of mechanized processes transitioned most economies from being based in agricultural to being based on industrial processes, hence the term industrial revolution. The second industrial revolution occurred roughly 100 years later in the late 19th century and was driven by many inventions, including the AC power grid by Nikola Tesla, the automobile by Carl Benz, the airplane by Wilbur and Orville Wright, the telephone by Alexander Graham Bell, the light bulb by Thomas Edison, the process for mass producing steel by Henry Bessemer, and the assembly line by Henry Ford. Tim's now going to provide us a brief background on the third industrial revolution and set us up for conversation regarding the fourth industrial revolution.
Thanks, Rob. Greater accessibility to computers was the driving force behind the third industrial revolution. Initially, the computers were too big, too expensive, and had limited capabilities for use on the factory floor. In 1969, with the invention of the PLC by Dick Morley, it became possible to have computers on the floor. Incredibly, the ladder logic that was used for programming in those first PLCs is still being used today, 52 years later. Moving on to the mid-90s, the introduction of Windows 3.1, a graphical operating environment, brought computers full scale to the factory floor. So if we move on from the third to the fourth industrial revolution, the fourth industrial revolution is a combination of many technologies, including cybersecurity, big data, Internet of Things, AI, machine learning, system connectivity, and cloud computing. So Rob is going to continue and set us up for how we're going to present the information going forward.
Based on questions that we've received from you leading up to the webinar, we're going to discuss the topics that Tim just mentioned in more detail. And then as time permits, we're going to be addressing more questions that you guys provide us in the chat window today. Don't forget, we've got the chat window on the side to address any questions. So anything that comes up, feel free to ask us. For each topic, Tim's going to provide a brief background and then pose a question or a problem to Rich, who will then answer it for us. And then we'll transition to the next subject. Our first topic of conversation that Tim's going to now discuss is cybersecurity.
Tim, you muted. Tim, you muted. Sorry.
Experts predict that in 2021, so-called successful ransomware attacks will occur every 11 minutes. When you hear statistics such as this, you consider how many companies are affected, and it seems overwhelming. Based on this, hackers are not likely picking their targets, but rather using a spray and pray approach, sending out mass amount of attacks to see what sticks. You might think that hackers would target companies that are bigger and more profitable, but this is not necessarily the case. By going after companies with weaker security systems, they increase the chances of success and the corresponding payday. For the flavor and fragrance industry, production control systems are connected to ERP, regulatory systems, and quality, and also to robotic and PLC-based automation. The integration between these systems and IT systems and the cloud creates significant security issues and business risks. Rich is going to go into more detail on what can be done about this.
Thanks, Tim, and good morning, everyone. We're really happy that you joined us, and we just happy to be here. So as Tim mentioned, that cybersecurity is a big issue, and just this last year or so, we know of a few of our flavor and fragrance customers that have had a breach by a ransomware attack, and it's been quite devastating for some of these clients from a productivity loss. Forget about the business side of the world. We don't know about that, but we know from a production point of view, there's been some big impacts. So we believe that of all things, this is probably the top priority because these attacks are happening more and more often, and it's happening, like Tim mentioned, I think every 11 minutes there's a breach made at some place. So what we want to do today is talk about other technologies that are coming out in the last year or so. So there's one of the major networking companies has come out with this product that works specifically with industrial networks. And what it does is it will have this system, this component that will go onto your industrial network. Once it's on that network, it's going to start listening and identifying all the different devices that are on your industrial network. Once it's identified those devices, it's going to listen to how they talk to each other. So for example, if there's a PLC CPU and there's a remote IO panel and they're talking Modbus TCP IP between them, it's going to say, oh, okay, what's this protocol? It's going to identify it as Modbus TCP IP. It's going to check this is a safe, normally used industrial protocol, make that acceptable, and it's going to go around the whole device network and identify all these different subcomponents, because not everything is talking Modbus. They're talking different, you may be talking a different protocol to a different device. So it's going to identify all the protocols, all the devices, and it's going to print out a map, and it's going to identify vulnerabilities for you to exist, for you to take an action on. So once you've set up your system and you've now gotten this map, you're going to be able to segment different parts of your industrial network. So for example, if that CPU is connected to 4 different remote IO panels, all of them talking Modbus TCP IP, what's going to happen is going to be able to draw, and I don't know actually how it works, but you draw a section. That segment is now going to be bordered off. So as you turn on the system and the system's actually working, the cybersecurity system is going to be logging everything like a black box for an airplane, and it's going to be monitoring all activities. So if a new device comes on or a new protocol starts talking on that network, it will shut down that segment and treat that as a breach. So that breach doesn't make its way in through this area and then go through the rest of the industrial network. So there's some great new products. And if you want more information, we could get you some information, but that's not our main focus at InItech. So Rob, I know we got limited time. So what's our next?
Yep, and it's great to see that, you know, with the increased cybersecurity threat, there's definitely technology being out there to give us a little bit of ease. Our next topic of conversation is in regards to the Internet of Things and big data. Tim, can you give us some background?
So big data refers to information that's stored in the cloud. It's a massive and complex data set, both structured and unstructured. They're generated rapidly and transmitted widely. This leads us now to the 3 V's of big data: volume, the huge amount of data that's incorporated into this; the velocity, which is the speed that's required to process and analyze the volume of data that's out there; and also the variety. So data can be coming from many different sources, including text and video, audio, and numbers. Traditional tools are not equipped to handle the complexity and the volume of this big data. So software has been developed specifically for this purpose. So if we move on to the Internet of Things, or IoT, significant data, not necessarily the big data that I was just talking about, is a result of IoT. It's a network of physical objects with embedded sensors, software, and other technologies that can connect and exchange data over the internet. The things could be as simple as household devices or as complex as business systems. 10 billion of these things are currently in use. Experts predict that by 2025, there will be 22 billion of these things out there being connected. So Rich is going to talk a little bit more about what this big data and the conductivity means.
Okay, so let's take a look at your existing data right now before we get into the big data and IoT topic. So in all the facilities we work with, there is some type of database for transactional data. So transactional data is if you were to go and have a batch that you're making and you need to add a raw material, you actually take the raw material, you take the lot number, you pour that amount. So you're adding those transactions of what was the material, what was the batch, what was the customer. All that information is now being logged into a transactional database, typically like a SQL database. Some of our clients also have what's called a process database, also known as a historian. So what that historian does, it takes process-related data. So if we use the example of a vanilla still has vacuum, temperature, there's a variety of maybe agitator speed, there's a variety of different components that are in there, and that temperature, vacuum values, they're going to be logged every few seconds. So now when we go back and look at the history of what happened in that batch, we can see a temperature ramping up, holding and soaking, and then cooling off. So that's a curve that we want to hold for that particular process. So now if we take a new device, let's say a temperature transmitter, and that temperature transmitter is IoT. So it's got the ability to not only talk to the PLC in the control system or a single loop controller, it's got the ability to go up to the cloud and report information. So what this device, this IoT temperature transmitter will do, it will start streaming data back up to the cloud about what's going on, what's its health, what's its temperature right now, and it's going to be logging all this information along with thousands and thousands of other devices from that manufacturer into this big data database. So what's going to happen up there is they're going to be able to do some analytics. So based upon the range of that temperature probe, what is the life expectancy if you run at the low end, the middle range, or if you're at the very highest end on that temperature probe? Is there any changes in life expectancy? So for your vanilla still problem, say you're running right at the middle ground of where that temperature probe is supposed to be, and your life expectancy is 10 years, 5 years, whatever it is. So this company is going to be able to feed information back to you as to when you need to calibrate that instrument and when they expect failure to occur. And they can send you information, say it's a 10-year life, a 9th year, they can send out an email, we're expecting your temperature probe to fail within this next 12-month period. And then you have time to do preventive maintenance because you've had predictive information coming at you, and you can replace that temperature probe and not have the situation where the probe fails in the middle of a batch, and then you have downtime and you maybe don't have a spare and you have to overnight one in, or if you're in today's environment where supply chains all discombobulated, you're not going to be able to get that right away, and it could cause a couple of days of downtime. So so big data definitely has a place. It's not going to replace what we'll call local data or historian or process data, but the three of them can work well together to help you improve efficiencies in your plant. Rob?
Yep, and we see everybody all over the place is collecting as much data as they possibly can. And then our next topic of conversation is basically going to tell us how they're going to tap into that wealth of extra data. So the next thing we'd like to talk about is artificial intelligence. Can we get some background on that, Tim?
Sure. So artificial intelligence, or AI, is intelligence demonstrated by machines, as opposed to natural intelligence, which is demonstrated by humans. In its simplest form, AI combines computer science and robust data sets to enable problem solving. Subfields of AI include machine learning and deep learning. These comprise AI algorithms that seek to create expert systems to make predictions and classifications based on input data. Within AI, there's also three subcategories: narrow or weak AI, which performs a limited set of predetermined functions. As an example, think of a retail kiosk. General or strong AI, which is said to be equal to human mind's ability to function autonomously. And finally, super AI, which one day will exceed human intelligence and supposedly will take over the world. There's still a lot of hype, though, with AI. According to Gartner's hype cycle on innovations, the typical progression is from overenthusiasm to disillusionment to an eventual understanding of the relevance of the information or the innovation and its potential role in the marketplace. Lex Friedman, in a lecture at MIT in 2019, said that AI is at the peak of inflated expectations and approaching the trough of disillusionment. So now Rich has got a nice little video to show you that will highlight the point.
Okay, thanks, Tim. So we're going to use your example when you talked about general or strong AI and an autonomous vehicle. So let's take the example of a Domino's Pizza vehicle. So with that scenario, there's a computer that's plugged in. And again, this computer has no human direction. It gets plugged into this machine, this car, and it starts going out and checking all the sensors. So when it's checking the sensors, it says, oh, okay, I got an engine, I got temperature from my engine, I got wheel speeds, I got blinkers, I got an oven that I'm controlling, and I start to figure out what I am. Okay, I think I have all these things. I guess I must be a car. So then in that car, I have these ovens. Why do I have these ovens? Okay, maybe I'm a pizza delivery car. And then what that pizza delivery car does, it starts to test and validate. Okay, let me turn on the engine. Let me try to move forward. How do I stop? How do my blinkers work? How do I get all this information about when I'm supposed to stop at a red light? What does a red light even mean? Because that is information that hasn't been pre-programmed by a human. So it's got to go out and it's got to figure all these things out. So let's just say that can actually do that. So it says, okay, the best pizza comes from Naples, and I have 800-degree ovens. So I'm going to set my temperature. I'm going to take that. And I'm going to get told to go to 14 Main Street. So at 14 Main Street, we have a delivery of so many pizzas. And we go there. Maybe there's facial recognition. Maybe we got to wait some way to identify the person coming to get a car to get those pizzas. Once we make those pizzas, then we're often going back to get the next delivery. So that's theoretically how AI works. But I think there's some things that you have to take a look at too. What if that computer kind of thinks like a 5-year-old and it has no ability to think about fear, no ability to think about going slow because it likes to go fast. So how does that computer now program itself? It now views its trip to 14 Main Street not as I'm delivering pizza, it's now going to be a race. Who gets to 14 Main Street the first? It has no idea what red lights are because it doesn't care, because it's all about going fast. And then from a safety point of view, sometimes it may not care because it thinks it can just jump back on course again and continue on the process. So I don't think that AI is really ready. Maybe it's someday, but right now I don't believe it's ready at all. However, I do believe that machine learning is what a lot of people are referring to as AI these days. And we have machine learning in most of our facilities that we have right now. So if we look at a robot that's pouring materials, or we have a bulk pouring system that is automatically pouring into your mixed tanks, there's going to be some closed loop feedback system. So when you have a value that you're supposed to pour, it's going to send it down to a controller of some sort, which is then going to say, I need to pour X amount of value, kgs. And then when you start to pour, the system is going to look at the values coming back from either the flow meter or the load cells. So let's just say we're going into a larger bulk tank. So now as that flow is occurring, the PLC is updating every few milliseconds, say 4 or 5 milliseconds, and it's checking how much material has passed through in those 4 milliseconds, those 5 milliseconds. So it's now checking the flow rate, and it's going to predict now when it should turn off that valve or get that 100 kgs we're supposed to be pouring in there, 1,000 kgs, right? So, but it also knows that that valve at the end that's turning off is a physical device. And say it's an angle body valve and it takes 200 milliseconds to shut. So when you send that signal, we're going to have 200 millisecond delay before you actually turn it. So you're going to actually move your set point back 200 milliseconds. But then we also have a little bit of material left in the pipe and some dribbling effect. So we need to deduct that amount too from when we're going to trigger that closing point for that valve to close. So when you're complete that pour, and it's supposed to be 1,000 kgs, and you're 1,000.02 kgs, still within the acceptable range of accuracy. But the next time it pours, it may adjust that so you don't have that tiny little bit of overpour. So it's a smart system. It's doing machine learning already. And I believe that machine learning is going to only expand and be more helpful on the shop floor.
Thanks, Rich. The next conversation that we're going to have is in regards to system connectivity, and Tim's going to give us the background on that now.
So I think with ever increasing things, as we talked about before, and ever increasing collection of data, it becomes more and more important to be able to connect these systems together. So application programming interface, or API, is a software intermediary that allows two applications to talk to each other. So imagine for a minute that you're sitting at a restaurant, you have a menu, you generally have no direct connection to the kitchen. So a critical link is missing. How does your order get to the kitchen, and how does your food get to the table? In this case, the waiter is the equivalent of the API. He or she takes the order to the kitchen and returns the food to you, and hopefully everybody is satisfied. Another example of API is in the airline industry. So if you're interested in taking a trip, you can go directly to an airline's website, and you can look up flights, you can look up times and dates and other options, and you can book the ticket on there. But an alternative that many people use is using a service such as Expedia. So this Expedia in this case is really the API, because you are going on their website and you're going with that same information for the days and times you want to go, the options you want. You're going on there and you are providing that information to them. They then in turn are looking at the airline's website to try to see if there's a match between what your requirements are and what the airline can provide to you. So in this case, again, that service provider is really the API, and the transaction gets completed based on the fact that that connection can be made. And so when you talk about industrial systems, this connection is critical to the success of the ongoing system. So Rich is going to provide a little bit more detail on this.
So thanks, Tim. So the connecting of systems is a super important component of Industry 4.0. So if we look at a real world example for one of the companies in this industry, the last week or two or three had an issue where they put the right label on the wrong product. They sent out a bunch of jerry cans or drums, whatever it was, to a client. The client put that into their batch, and that batch was rejected because it had the wrong product in there. So let's look at how connectivity could have helped that scenario. Because initially you have an ERP system, an order that comes down, they got 20 containers of some sort, and you're putting those pre-printed labels into a folder. So those folders get mixed up. You have someone double checking things. However it happens, things do happen. So the system you have there is just the ERP system and perhaps a regulatory system for GHS. And do they talk? Is there a separate label printing? I don't know all the processes between there, but those are systems that are happening to get this these product out the door. So if we were looking at connecting systems, the order comes into the ERP system. Once the order is in the ERP system, it drops down to a shop floor or MES system, where that's going to take that process order, that batch order, and it's going to go and help fill it. But then when it's actually compounded, going through QC and getting ready to be packed off, will be connected to that QC system as well. So as soon as that's approved, they say, okay, it's ready to pack off this material, and it's going to go into 20 different containers, and we're going to be connected to regulatory. Going to already have this information brought down, ready in the queue. And then once that information is ready in the queue, it's going to connect to the scale. So when we pour, we're going to know exactly how much was poured into that container. And then we're going to be connected to the printer, and we're going to be able to print out that label right then and there. And if there was a separate third-party printing software, that's going to be triggered to print that label. And then as you cap that or put the top in the drum, you're going to have the GHS label, and you're going to put that GHS label on that container. And then you're going to go to the next one. So then after you're done with 20 containers, you're going to post that information back to the ERP, exactly how much you packed out, what was the yield lost, actual versus reality, based on prediction. And then you have no manual entry, data entry mistakes as well along the process. So connecting systems could be super valuable.
Thanks, Rich. And it looks like we're probably going to have time for one question that we received in email prior to the start of this. The question is, what Industry 4.0 technologies, will Industry 4.0 technologies replace lean, or will they coexist?
So let me just add my part on this, and Rich can chime in. I think lean has been the dominant tool that's been used within flavor and fragrance industry for sure, in most industries over the last 20, 30 years, really trying to do continuous improvement and making improvements in making your process more effective. So, I think with the advent of the technologies that are coming along with 4.0, for me, it just enhances that, because, a lot of the data collection and the tools and stuff that were used in lean in the past were more manual, but now having the ability to collect all that, having the ability to analyze it, just really enhances the usefulness of the lean tools. So I think there's no question that 4.0 is going to accelerate the improvement activities within the flavor and fragrance industry.
Thanks, Tim. And I think if we use that example that we just had about the 20 different containers, I think that my thoughts are that lean is the engine on the train, or the toolbox for other tools to go into. So Industry 4.0 has a bunch of tools as a subcomponent of Industry 4.0. So if we looked at the connecting systems component of Industry 4.0, if we have a lean project of how do we fix mislabeling from not happening in the future. So what we can do is we can identify waste through the lean process. So how to get rid of the non-value added work, like pre-printing labels, having somebody go out and find the right folder, having a second person come in and double check to make sure the right labels are going on the right materials, having to go and do data entry for manual entry back into the system. So I think that lean is not going away. They're completely compatible. It's really thinking about what components of Industry 4.0 are going to most help your facility. So
thanks. Yeah, and I think that those are both good answers. So it looks like we're coming to the end of our presentation today, and we just wanted to make sure that we could reiterate the main points. And Rich, if you could bring up our slide again and then close us out, and then we'll have a nice ending to our meeting today. Thank you, everybody, again.
Okay, so let's go ahead and share this and look at okay, so our 4 stars of Industry 4.0. What are the things that we think are most important? Cybersecurity, number 1, because if you get an attack and they shut you down, it's better to protect yourself. So I think that's we think that's the most important component of Industry 4.0. I think machine learning is another really important component. I think that you should take advantage of that whenever that opportunity to have smarter machines work for you and help improve your productivity. I think connecting systems is an absolute, right? And obviously connecting systems can't exist if you don't have the right cybersecurity in place, but connecting systems just makes life easier. Why not have systems, computers talking perfectly to each other, because that's what they can do perfectly. Maybe not deliver pizza properly, but they can work really well. And then IoT, you have this predictive predictive maintenance. All that information is good information to have. So I'll turn it back to you, Rob, and you can close us out.
Before we end our conversation today, we just wanted to reiterate how important continuous improvement is to us, and we'd love to hear your feedback on how this webinar worked for you today. Any feedback that you have, please send to rich@initechinfo.com. From everyone at InItech, we want to thank you for joining us today, and we want to let you know that we'll be doing this again in the future. So please look out for information on our next webinar in the months ahead. And again, have a great day, and thank you for joining us.
Thanks, everyone.